Welcome to The Explainer. Today, we are diving deep behind the scenes of the internet, into a world of glass threads thinner than a human hair that are carrying our data at, well, literally the speed of light. We're talking about fiber optics, and you are not going to believe the kind of precision it takes to keep our digital world online.
Look, our need for data is just exploding. We're now moving into terabits of information flying around every single second. At those kinds of speeds, the glass fibers carrying all that data, they have to be absolutely perfect. There's zero room for error because even a flaw you can't see can cause a total failure and bring a whole network to its knees.
So how in the world do you test something that demands perfection? The answer is this really meticulous process called Tier 1 certification. You can think of it as the gold standard, the ultimate benchmark for making sure the physical backbone of the internet is healthy and ready to go. But before any of that testing can even begin, technicians have to face off against a really tough opponent. It's an invisible threat that is, without a doubt, the #1 enemy of any fiber optic network.
You'd probably think the biggest risk is some kind of complex hardware meltdown or a nasty software bug, right? But nope. Research from major players in the field shows that the leading cause of network outages is actually something way more basic.
The #1 bad guy? It's just dirt. That's it. Simple, everyday dust, the oils from our skin, and other tiny contaminants are the main saboteurs of our super-fast digital lives.
And to really get why that is, you have to zoom in, way in. The actual core of a single-mode fiber is only about 9 micrometers across. That is smaller than one of your skin cells. So a single speck of dust landing on that surface, it's like a giant boulder suddenly blocking a 6-lane highway.
So when you plug two fiber connectors together, any little bit of debris gets crushed right into the glass. And that just starts this whole chain reaction of bad things happening. The signal can get absorbed, or even worse, it can get reflected back where it came from, which causes all sorts of instability. Hard particles can permanently scratch the glass, and in really high-powered systems, that dirt can literally be fused into the glass, creating a blockage that you can't fix.
The only way to stop this microscopic chaos is a simple but absolutely non-negotiable protocol. Inspect, clean, inspect. Technicians use a special microscope to look at the connector, they clean it with optical-grade stuff, and this is key, they inspect it again to make sure it is perfectly, absolutely pristine before they make that connection.
So, let's say you've done all that. You've got a perfectly clean connector. Now what? How do you actually measure the performance of that fiber link? Well, for that, you're going to need a pretty specialized toolkit.
The test really comes down to two key instruments that work as a team. First, you have an optical light source. It's basically a highly calibrated flashlight that sends a super precise beam of light into one end of the fiber. Then, at the other end, an optical power meter acts like a precision detector, and its whole job is to measure exactly how much of that light made it all the way through.
Now, the power meter gives you a reading in a unit called dBm, which measures absolute power. Just think of it like a sound meter that tells you the exact volume of a speaker in a room. It's just a raw measurement of how strong the signal is. But for certification, what we really care about is loss, and that's measured in decibels, or dB. This doesn't tell us the final volume. It tells us how much volume we lost between the speaker and our ear. It's all about the difference between what we sent and what we actually received. Okay, now we're at the most critical step in this whole entire process, setting up a perfect baseline so we can actually measure that loss.
You know when you go to the grocery store to buy some apples? Before you weigh the fruit, you put the empty bag on the scale and you hit that tare button to zero it out? It's the exact same idea here. In fiber testing, you have to zero out your test cables so that you're only measuring the link itself, not your own equipment.
So technicians have a few different ways to set this 0 dB reference. There's what's known as a 1-chord, a 2-chord, and a 3-chord method. But for the best accuracy you can possibly get, all the industry standards bodies like the TIA and the IEC, they all strongly recommend one method over all the others.
And this is it, the 1-chord reference method. It's just beautifully simple. You connect one high-quality test cable directly from your light source to your power meter. You let the source warm up and stabilize, then you push a button to tell the meter, okay, this power level right here, that's our 0 dB reference. Then, and this is super important, you only disconnect the end that's plugged into the power meter, leaving the source connection completely untouched for the rest of the test.
What you're doing here is brilliant. By connecting the source directly to the meter, you're creating a nearly perfect, almost lossless connection. This sets the highest possible standard for your baseline, which makes sure that you're going to measure every tiny little bit of loss in the actual link you're trying to test.
So why is this the gold standard? Well, it's the most accurate because it has the lowest possible measurement uncertainty. And critically, it forces the test to include the loss of the entire link, and that means the very first connector and the very last one, which is a huge deal on shorter links where those connectors are actually the main source of loss.
And you can really see why it's so much better when you compare the methods. The other two, the 2-chord and 3-chord methods, they actually include extra connections while you're zeroing everything out. That basically hides some of the loss from those connections, which gives you a final result that's way too optimistic and just plain inaccurate.
And here it is visually. It's crystal clear. The more connections you add to your reference setup, the higher your potential for measurement error becomes. The 1-chord method is all by itself down there with the lowest uncertainty, making it really the only reliable choice for a proper certification. Okay, so the reference is set, the link is connected, and the measurement is taken. This is it, the moment of truth.
That final dB reading gets compared against a pre-calculated number called a loss budget. You can just think of this as the pass-fail line. It's the absolute maximum amount of signal the link is allowed to lose before its performance starts to suffer. If the measured loss is below that budget, the link passes. Boom! It's certified and it's ready to carry our data at the speed of light. You know, there's a saying in this industry that really fits. Accuracy is no longer a luxury, it has become vital. And that is for sure.
From inspecting for microscopic dust all the way to choosing the right reference method, this whole process is just an amazing testament to the incredible precision that holds up our modern world. It's a pretty powerful reminder that the biggest things we rely on, like the internet, often depend on getting the absolute smallest things perfectly right. So it makes you wonder, what other hidden systems are out there, quietly and perfectly powering our world?